Almost every developer seems to be using this variable incorrectly. It is used in all of your favorite video games, and you'll find it in every game engine from Unity to Unreal to GameMaker to Godot, which makes it even more frustrating that all most developers know about it is
I should multiply everything by delta time. If not, I am committing a crime.
LOL. If only it were so easy, huh? And if you're one of those know-it-alls who thinks they know everything already, then grab a pen and a piece of paper. I will test your knowledge. You're writing a game development test, my friend, and I will grade you at the end of the video. This is not a joke. Yeah? Well, no, videos create the illusion of motion by showing you a bunch of images very quickly, and games work the exact same way, but there's one important difference. In a video, all of the images have the exact same length. So for example, if you have a video with 25 frames per second, then one frame is shown exactly every 1 divided by 25 seconds. For games, unfortunately, it's a mess. All of the frames are just shown whenever they finished rendering, which can be whenever. In a video, if we want to create the illusion of motion, we can just move the character by the same amount every frame and it will look like a smooth motion. In a game, because all of the frames are spaced apart differently, we cannot do that. Dear test participants, write me a line of code that makes a character move over the screen with a consistent speed. You have 3 seconds to lock in your final solution. 3, 2, 1. Here's my friend Jerry. He has a very good computer, so his game runs with 60 frames per second. And this is Betty. She just loves toaster, so she's playing this on a toaster and only has 5 frames per second. Oh, what do I see here? Is this your final answer? The update event is called every frame. This is the position of the snail. And you want to go to the right, so you multiply the right vector times your movement speed, how far you want to move each frame. So that up there is your solution. Let's run it and see what happens. Jerry is zooming away and Betty is left behind. You monster, what have you done? So obviously that's because both snails move the same amount each frame, but Jerry just has way more frames per second, so obviously he's gonna move fast. I'm pretty sure you're not a criminal though, cause I'm pretty sure you remembered
I should multiply everything by delta time. If not, I am committing a crime.
Let's do that then. Let's multiply in this magical variable that we don't quite understand yet. And all of a sudden it works. If we keep this running forever, they will always stay next to each other. So if you're participating in the test and you got this correct, then you get 10 points. Write down your points. The question is, why is this solution correct? Let's have a look at our film strips or game strips. And for this example, we actually do have consistent time intervals between the frames. For Jerry, it's about 16 milliseconds between each frame. And for Betty, it's 200. And what you can kind of intuitively see here is that the more time passed since the last frame, the further we have to move the character, and there is a direct correlation. So delta time is exactly that. It is the time distance between frames. If it's been twice as long since the last frame has been rendered, we need to move twice as far. How delta time is measured is a little different from game engine to game engine. In Unity, it's measured in seconds. So that means Jerry's delta time is 0.016 and Betty's delta time is 0.2. If we multiply that into our equation, Betty moves way more than Jerry every frame, which is exactly what we need. In a real game, the frame rate will obviously vary. Sometimes you'll have 60 frames per second, sometimes you'll have 5 frames per second. So that is important to know. Delta time is automatically recalculated every frame, and it's usually different every frame. That way it's possible to go back and forth between being Betty and Jerry, and it's still gonna work out just fine. So little know-it-alls, what do you think is delta time exactly? Is it A, the time elapsed between the last frame and the one preceding it? B, the time elapsed between the frame currently being processed and the one preceding it? C, is answer B plus the time since the current frame started? Or is it D, the time since this object last accessed the delta time variable? So dear test participants, think about it, pause the video, there are some points to be earned. I will reveal the solution in 3, 2, 1. If you picked any of these two here, then haha, I trolled you real bad. B is not the correct answer either, but I'll give you 10 points, cause it's almost correct. Why is it only almost correct? Well, let's say we're here in the timeline and we're currently running our program code to calculate the next frame. In that case, we actually do have a problem, cause we do not have the next frame yet, nor do we know when our calculation's gonna be finished. So really the only thing we can do is use the delta time from the last 2 frames and use that for our calculation. Is this the exact number we're looking for? Well, definitely not, but it's usually a reasonable assumption that's at least roughly in the correct ballpark, and we're still gonna use this interval as the delta time in the next frame, so it's gonna even itself out in the long run. So if you picked A, then I'm actually slightly impressed and you get 20 points. Congratulations. What that means is delta time always has a 1 frame delay. Now there's a fun little experiment you can run in your game engine. You can create an artificial lag spike. I'm personally doing that by running a bunch of unnecessary computations a bunch of times. So whenever I press X now, the game will have a huge lag spike. Here we have the two brothers, Jerry and Barry. Barry unfortunately suffers from lag spikes. As we're using delta time, he can always catch up though. Let's watch one of Barry's lag spikes frame by frame. As you can see, he's moving a little bit every frame, and all of a sudden the lag spike hits. So because of all of my unnecessary computations, the next frame takes way longer to be calculated. But what do you think will happen in the next frame? Take your guess. Actually pause the video and take a guess now. You can earn 10 points if you get it right. The solution in 3, 2, 1. Here it is. I'm playing the same 2 frames over and over again, so you can see just those 2 frames. And as you can see, it's moving a little bit, a tiny little bit. So if you guessed anything like it moves a completely normal amount, then you get 10 points. And only in the next frame the expected teleport forward occurs. Why is it important to know that delta time always has a 1 frame delay? Well, honestly, it's only really useful for debugging and for avoiding your own confusion. So now you know how it works. For our next challenge, we want to achieve the same result. We want both snails to move at a consistent speed, but this time we want to code into fixed update instead of update. Don't worry, these are still the very easy questions. For those who don't know, fixed update happens a fixed amount of times every second. The question is, what do we have to change here to make this code work? Pause the video if you want to, and I expect your answer in 3, 2, 1. We, of course, need to remove the delta time. Oh, you're really racking up the points there. When we run our code in update, then this is where our code is executed. Or I guess to be a little more precise, not all of that is taken up by the update events. A huge portion of that is also taken up by rendering. But sometimes the irregularities caused by the system can be quite annoying to work around. That's why most game engines offer a separate system where you can execute code. In Unity, those are called fixed updates. And let's, for example, say we're executing some code right here. Why would we ever want to multiply anything by this interval right here? There's no freaking way that makes sense. If anything, then we want to multiply by this interval right here, which is called fixed delta time. So that means if you answered my last question with fixed delta time in the solution, then that's obviously correct as well. Multiplying the same static number that never changes into everything you do is obviously a little bit pointless, so you really don't have to. If fixed update is so much easier to use and we don't have to worry about delta time, why don't we just code our entire game in there? Well, actually that is a valid coding style as long as our code doesn't take too long to execute. But if it takes longer to execute than our fixed delta time, then we are in trouble, cause then our game starts slowing down. Also, what about Emily with her high-end gaming PC? Maybe she wants to run the game at a higher frame rate than the random number you decided on. So that's why usually using update and delta time is the more resilient and scalable system. But fixed update still has its place. For example, in Unity, anything physics related you usually want to put in the fixed update. That's because the physics engine is running in the fixed update as well. And that way your interactions with the physics engine are gonna be more consistent and more reliable. To make things more confusing, you can also turn the main update into a fixed update by adding weighting to your equation. So you can essentially set a fixed frame rate and then just wait for the remainder of the time. So in Unity, if you limit the frame rate to 60, that's pretty much exactly how that looks like. Some game engines even work like this by default. For example, in Game Maker, this is pretty much the default way everybody writes code. And once again, the cool thing is, as now all frames are spaced apart evenly, you don't necessarily have to use delta time anymore. The only problem is, of course, once again, there's no such thing as a negative waiting time. So if your update and rendering take too long, then you're in trouble. Take a deep breath, take a sip of water, go on a toilet break if you need to, cause that was the easy part. I downgraded Betty's toaster to 2 frames per second so we can a little more easily see when something is wrong. And this is what I would like you to create. Snails start with a speed of 0 and then their speed linearly increases over time. They do not have to loop around. I'm just doing that for demonstration purposes. The only thing that matters is that every time Betty updates her position, she needs to be exactly next to Jerry. Just as before, we're using the same script for both snails, so you cannot write separate scripts for both of them. You have to write your code in update and you have to use delta time. So I want them to start slow and get faster and faster. Pause the video now and try to come up with a solution. You have 3, 2, 1. Okay, let's see what you got. So you have 2 variables. That's nice. Yeah, you have an acceleration variable and you have a speed variable. Very good. So this part is the exact same thing as last time. And the only thing we added was this line here. We add something to the speed. And now here we take the acceleration and we multiply it by delta time. So this is for movement. This is for increasing the speed. And both times we multiply in delta time. Okay, I loaded in your solution. Let's try it out. And uh-oh, Betty, hurry up. Let's check this out in slow motion, where Betty updates to... she's too short. Okay, then I guess we have to move this before. So first we add something to our speed, and then we use that speed to accelerate ourselves forwards. Come on, stay next to each other, please, please. Go, go, go. And this time, Betty is ahead. What the hell? This time it's the other way around. But when Betty updated her position, they were definitely not next to each other. So if you got any of the solutions we just talked about, then you only get 20 points. Because this is a good approximation, but it's not entirely correct. Okay, then, so what happens if we apply half of the acceleration before and the other half of the acceleration after we move the snails? Accelerating before the movement didn't work, accelerating after the movement didn't work. So let's try splitting it in two, I guess. Will our random solution work? The tension is immeasurable. I need a little more hype here. Come on, more hype, more hype. What? It is perfect! There's one interesting question, and that is, why? Why does this work? Let's graph this out. On the x-axis we have the time, and on the y-axis we have the speed of the snail. So our snails start out with 0 speed, but they do get faster and faster over time. Luckily for every frame we know exactly how fast the snails are, cause the speed is just increasing linearly. So now let's have a look at our first slightly incorrect solution again. The linear increase of speed is something we don't really have to worry about. That's working correctly. The more time passes, the more we increase the speed. Very straightforward. This is the part of the code that is responsible for calculating how far the snail moves. So now let's assume we're running this code right here in between those two frames. What are we multiplying? We're multiplying speed times delta time. By multiplying those two numbers, we calculate the surface area of this beautiful rectangle here. So the surface area of this rectangle represents how much we're gonna move between those two frames. So can you start to see the problem here? If our speed would look like this and was actually consistent, then that would look a lot more correct, wouldn't it? Because in that case, multiplying speed times delta time would create a rectangle that fills up the surface area under the graph perfectly. So we have to take into consideration that the speed is constantly changing, and what that means is we're lacking a piece here. Or in other words, we're not moving enough. Okay, then I guess we have to move this before. So first we add something to our speed, and then we use that speed to accelerate ourselves forwards. Well, okay, so in that case, instead of using this speed, you're telling me we should use this speed, which results in this surface area, which is too much. We are moving too much now. We really just want the area under the graph. So how do we get that? Well, hey, there's an entire field in math. The thing you want to research are integrals, or more precisely definite integrals, which have a start and an end point. Luckily for this specific case, there's an easy hack we can apply. We can chop off one corner and attach it back like so, and we have a rectangle. As you can see, the speed we want to multiply by is exactly in the middle of the start speed and the end speed. So in this case, but only because the speed is a linear function, we dodged a bullet and we get away without doing any more complicated math. And that is exactly why this is a correct solution. This first line here gets us the middle point, and then this last line here makes sure we add all of the speed that we need to add. So if you got this solution or any solution that effectively achieves the same result, then you get 50 points! Woo! I feel like I'm probably clapping for nobody, but still, woo! And by the way, just a little addition or correction, this calculation is obviously not happening here. It's happening here because of the 1 frame delay on delta time. So that means we're oftentimes not moving the exact amount that we should, but with a 1 frame delay, we're always moving the exact amount we should, so that's actually completely fine. And before you go scream at everybody who makes this quote-unquote mistake, please don't, because this is a very good approximation, and 9 out of 10 times it's gonna get the job done just fine. Betty won't like this, but I'm gonna upgrade her to 30 frames per second for this experiment. The general rule of thumb is the higher the frame rates, the better these approximations work. So this is the exact same flawed code that we already tried out earlier, but as you can see, the snails do a really good job staying in sync with each other. Let's keep this running for a little bit just to see what happens. And what you can see is it's not so flawed after all. They're starting to get slightly out of sync, but it's nothing too crazy. Why is that? The reason for that is that with a higher frame rate, the speed is recalculated more often, and therefore we have a higher accuracy. Did I hear a complaint that you want more points for your answer then? Don't get greedy! Remember that depending on the circumstances, these inaccuracies can quickly add up and they can accumulate. So using approximations is fine. You should just be aware of the fact that you are using an approximation, which I feel like most developers aren't. And for everything anything where you do care about accuracy, like for example the player movement, from now on you know that you can probably do a little better. How can you do better? Well, I even made a slide for all of those rule lovers out there. Whenever a variable changes over time, then this is the mathematically perfect solution and this is the approximation. The thing is, you obviously only need this formula if the change speed itself is changing. If the change speed is consistent, then this is a mathematically perfect solution as well. If the change speed itself is changing, then you have to figure out the average change speed over the last delta time seconds. So let's for example say delta time is 0.5 seconds. Then you have to figure out the average change speed over that time period and multiply by that. This next mistake, however, is a really rough one, and I've seen people make this mistake, so that's why I have to include this in the video. All the experienced developers, look away, this might hurt. So I made this little game called Flappy Snail, which is essentially the exact same thing we just talked about. We're accelerating in one direction, and the only difference is that now I have a jump button. So in this case for movement we're using the approximation, which is fine, but I might have removed something very important from the jump code down here, and if you can tell me what's missing, then you'll get some points. You have 3, 2, 1, lock in your answer. And if this is your final answer, okay, don't lie to me, what's locked in is locked in. And then you get minus 10 points, cause this is so wrong. Oh my god, don't ever do this. This is horrible. You wanna multiply by delta time when something happens over time. When something happens immediately, like a jump. That is a point in time. When something happens at a point in time, you never want to multiply by a period of time. That just doesn't make any sense, unless you want to jump twice as high when the frame rate drops or something. But why would you ever want that? Why? Alright, I'm sorry for your loss if you fell for it, but if you were either confused or you were like, seems alright to me, then you get 10 points. Luckily, there's an incredibly catchy rule. Just say it with me.
I should multiply everything by delta time. But only once and not accidentally twice. And only when we're not in fixed update. And only when it's something that is really happening over a period of time. If not, I am committing a crime.
Oh yeah. And don't freaking mess up your freaking Lerp functions, you OMG, just use your brain, WTF. And that is exactly why rules stink. There are too many exceptions. But what was that? Don't mess up your Lerp functions? I think we should look into that. If you don't know what a Lerp function is, then this is probably not the best video to explain it, but I'll give it a brief shot. It allows you to interpolate between A and B with the value t. T has to be a value between 0 and 1, and the calculation happening underneath is fairly simple. It's just A times 1 minus t plus b times t. So let's for example say you have two positions on the x-axis, -7 and 7. So that means if you set t to 0, you'll end up with -7. If you set it to 1, you'll end up with 7. And anything in between will give you something in between. Now using a Lerp function, I would like you to create this. The snails start out fast, but they get slower and slower, and they never fully arrive at their target destination. They're just getting closer every frame, but they will never arrive there. And I'll even give you a little tip. You can do this with a Lerp function that can interpolate from one position to another. The only thing you have to fill in is this last parameter of the Lerp function here. This is the snail's current position, this is the snail's target position, and this is what you gotta fill in. By now you know how we roll. We're looking for the mathematically perfect solution only, so no pity points for approximations this time. This is your final test. Here's once again what to create. And of course, whenever Betty updates, they need to be exactly on top of each other. Pause the video and you have 3, 2, 1. I'm actually gonna split this into 2 lines. Let's put in a blend variable here. And I'm sure the solution most of you got is just time.deltaTime multiplied by Lerp speed. Honestly, I don't even have to run this to prove to you that this can't possibly be correct. Because I told you, the snails never reach their target destination. But what happens if we have the giga lag spike of doom and we have a 2-second lag spike? There's nothing stopping this blend value from becoming really large, even larger than 1. And what happens if t is 1? Then we instantly jump to our target position, which is wrong. Alright, so let's run the simulation and see how long it takes for those 2 snails to get out of sync. And they're out of sync. That's not too impressive. So in these kind of scenarios, we have to realize that we are on an exponential function. In this case, on a reversed exponential function. On the x-axis, we have the time, and on the y-axis, we have the distance from the target. So you can see the distance from the target is getting lower and lower, but it's never reaching 0. As we are on an exponential function, we have to use an exponential function. Mind blown. All right, I'm just gonna show you the correct solution. Here it is, and it looks a little intimidating, I admit that. The 1 minus, we can remove that, but then we have to switch those two around. So let's do that to simplify that a bit. So we end up with 0.5 to the power of delta time times lerp speed, and that then is the number that we use to blend between our current position and our target position. On an exponential curve, what do you have to do when you want to move to the right? You have to change the exponent. And you can see the exponent is just linearly correlating with time. It's literally just counting up. And that's why we can just put our time in the exponent and call it a day. The 0.5, by the way, are completely arbitrary. You can choose pretty much any number between 0 and 1. If you got that correct, then damn, I'm impressed, and you get 50 points. And now I can hear all of the formula lovers crying, oh my god, why didn't you use the formula? Oh, don't worry, you can do that here as well. Instead of looking at the distance, you just have to look at the speed. And as it turns out, the speed is an exponential function as well. It starts out very fast and then gets slower and slower, but never reaches 0. And now if you got a time interval defined by delta time, then we just once again have to calculate the area under the graph, which we can do by multiplying delta time by the average speed within that interval. The only problem is that the average speed is no longer just the middle point between the start and the end point, because this time we have a curved graph. So if you want to get this correct using this method, then you gotta look into integrals. If you're still confused and you're like, what the hell? Then remember that using the much simpler approximation is usually fine. Also, I got a brilliant bonus tip for you. Test your game. One thing you can do in Unity for testing is set application.target frame rate, and I'll, for example, set that to 12 or something, which is relatively low. Feels very much like a slideshow. This is a little painful, but as you can see, everything's working and everything's moving at the speed it's supposed to and stuff like that. So just try it out. Just try your game at different speeds and see what happens. Most Unity users know about this, but you can actually pause the game by just setting Time.time scale. And if you set up your game correctly, then nothing should move anymore. This completely pauses your game with 1 line of code. It's also a good line to test if you implemented delta time correctly everywhere. All in all, don't stress out about it. It's not as difficult as it seems. But also don't be naive about it. You can't just multiply delta time into everything without even thinking about it and expecting it to work. That's not how it works. But it's also not rocket science. Here are your grades. Check out your points, count your points, and see what grade you got. And I'm Jonas. I usually make game development content. This was a bit of a different video for me. I actually make a bit of a different video every once in a while. I like mixing it up, otherwise I get bored. But in general, I make videos about game development. So check out my other videos, and I'll see you in the next one. Take care. Bye.
And don't freaking mess up your freaking lerp functions, you OMG. Just use your brain, WTF.